Have you ever watched a cat fall and land perfectly on its feet and thought to yourself, how on earth did that just happen? Because if a human fell from the same height in the same awkward position, we would not be walking away from that so gracefully. Cats do something that genuinely puzzles physicists, engineers, and biologists all at once. And today we are going to break down exactly what is happening inside a falling cat, using real physics, real science, and zero magic. By the end of this video, you will never look at your cat the same way again. Let us start with the problem that makes cat balance so fascinating in the first place. When an object is in free fall, it has zero net angular momentum. That is a physics principle called conservation of angular momentum, and it is one of the most fundamental rules in the universe. It basically says that if you are not being pushed or pulled by an external torque, your rotation cannot change. So if you drop something without any spin, it should stay without any spin all the way down. Logically, a cat dropped upside down should land upside down, but it does not. And that right there is the paradox that kept scientists scratching their heads for over a century. The answer lies in something called the falling cat problem, which is a genuine topic in physics literature. Scientists formally described this puzzle in the 1800s, and it took until the 1960s before anyone produced a mathematically satisfying explanation. The confusion came from people thinking the cat was somehow violating angular momentum conservation, but the cat is not breaking any laws of physics. It is doing something far more clever. It is exploiting the geometry of its own body. Here is where things get really interesting. The cat uses what physicists call a geometric phase, sometimes referred to as the Barry phase in quantum mechanics, but applicable here in classical mechanics too. The idea is that a system can change its shape internally and, through a sequence of movements, end up in a different overall orientation, even though no net angular momentum was generated. Think of it like this. Imagine you are floating in zero gravity with your arms at your sides. You cannot rotate your whole body by just tensing a muscle. But if you swing your arms in a specific sequence, bending at the waist, extending your legs in just the right pattern, you can end up facing a different direction than when you started. The cat does exactly this, but with extraordinary precision and in fractions of a second. The specific mechanism cats use is sometimes described as the tuck and extend method. The cat essentially divides its body into two halves, the front and the rear, and rotates them in opposite directions while simultaneously changing the radius of each half. When one section of the body is tucked in tight, it rotates quickly like a figure skater pulling their arms in to spin faster. When the other section is extended outward, it resists rotation. The cat alternates this tuck and extend between front and back in a coordinated sequence, achieving a net rotation of the whole body without violating the zero angular momentum rule. It is genuinely one of the most elegant mechanical solutions in nature, but the physics does not stop with the rotation mechanism. The cat also has a completely unique skeletal structure that makes all of this possible. Cats have an unusually flexible backbone compared to most mammals. Their vertebral column contains elastic cushioning between each segment that allows for extreme twisting and bending that would simply be impossible in a human spine. On top of that, cats have what is called a free-floating clavicle, meaning their collarbone is not rigidly attached to the rest of the shoulder structure. This gives their front limbs an enormous range of motion that allows them to absorb impact in ways that a rigid skeletal structure never could. Now let us talk about the vestibular system, because this is where the cat's internal engineering becomes almost unbelievably sophisticated. Deep inside a cat's inner ear sits a series of fluid-filled canals and tiny calcium crystals called otoliths. When the cat moves, this fluid shifts and those crystals press against sensitive hair cells that send electrical signals to the brain. This system gives the cat a real-time, three-dimensional map of its own orientation in space. It detects rotation, linear acceleration, and gravitational pull simultaneously. The cat's brain processes all of this information at incredible speed, essentially running a continuous physics calculation to determine where the body is and where it needs to be. The cat's eyes also play a supporting role. A cat's visual system has what is known as a strong righting reflex connection, meaning its eyes actively help stabilize its perception of the horizon. Even during a fall, a cat's gaze locks onto a stable reference point in the environment, which feeds additional spatial data back into the brain's orientation system, though the vestibular and visual inputs work together so that the cat knows exactly how much rotation it needs to complete before impact. And then there is the final act, the landing itself. Cats spread their legs wide as they approach the ground, increasing their surface area and lowering their center of mass relative to their support base. Their highly elastic leg muscles and tendons act like biological springs, absorbing and distributing the force of impact across the entire body rather than concentrating it at any single point. Studies on cats falling from various heights have shown something counterintuitive. Cats falling from greater heights sometimes sustain fewer injuries than cats falling from shorter distances because they have more time to fully complete the righting reflex and achieve a relaxed spread position before landing. What makes all of this genuinely remarkable is that cats are not consciously thinking through any of these calculations. A kitten as young as a few weeks old begins showing early signs of the righting reflex, and by around 7 weeks, most kittens can perform the full maneuver. It is largely hardwired into the nervous system, a piece of biological software refined over millions of years of evolution. The physics is complex enough that human engineers have spent decades trying to replicate it in robotics, and we are still not quite there. So the next time your cat leaps off a shelf and sticks the landing without even pausing to think about it, remember that you just witnessed a live demonstration of geometric phase mechanics, conservation of angular momentum, vestibular engineering, and evolutionary biomechanics all working together in perfect synchrony. Physics has never looked so effortless.